So, yeah, thank you very much, and thank you all for coming. So the title of the talk is the free dynamics of a tracer particle in a Fermi sea, and this project is based on joint work with Max Jeplik, David Mitruskas, and Peter Pickel from LMU Munich. Peter Pickel was my PhD advisor a while ago, and Max and David are current PhD students of his. And yeah, so maybe let me start by explaining the basic setup of this talk. So I want to look, as usual, at the quantum dynamics. So I want to look at the solution of the Schrödinger equation, I dt psi equals h psi, with the Hamiltonian, which looks like that. It is a Hamiltonian for n plus 1 particles, one y particle. So there's a free, there's a Laplace y, free Hamiltonian for the y particle. And then there are n, let me introduce masses also, 1/2 mx. There are n x particles, all of a similar kind with the same mass. And then there's an interaction with, say, some coupling parameter g between the gas particles, so the x particles, and the y particle. So in this Hamiltonian, I neglect the interaction between the gas particles, and I only have interaction of this one test particle or tracer particle or extra particle with the x particles, which I also often call the gas particles. And I want to look at a very simple situation here. So I'll take just the nicest kind of interaction potential I can think of. So here I will take a potential in C infinity 0. So compactly supported and infinitely often differentiable. It's not exactly necessary to make these strong assumptions. A couple of times differentiable, I think 3 or 4 will actually be enough for the main result. But let me just take the most simple case here. And so the wave function now lives in an n plus 1 body Hilbert space. Let me denote that by hn plus 1. And I want to take it in the following way. I'll have the Hilbert space of the y particle tensor the Hilbert space, the n particle Hilbert space of the x particles.
Could you write just a little bigger?
Yeah, sure. So the Hilbert space of the y particle is just the usual L2 space in the box in d dimensions. And the Hilbert space for the n gas particles, I want to take a fermionic Hilbert space. So it's the antisymmetrized L2 space on a box tensor n. So I have an antisymmetrization between the gas particles, but the one tracer particle is an extra particle that is not antisymmetrized with the other particles. And I'll always use periodic boundary conditions. So I don't want to look at any effects coming from the boundary. I just have periodic boundary conditions. And as an initial state, I would like to use something which comes closest to a factorized state, namely psi 0, which is just phi 0 living in the hy space, tensor state omega 0. And so as initial state for the gas, I just want to take the free ground state in a box. So omega 0 is just the antisymmetrized product state. Let me denote that by this wedge, j equals 1 to n of phi j zeros, where the phi j zeros are just plane wave in a box. Plane waves. Yes, the eigenstates in a box. So 1 over square root L to the d e to the I pjx. That's phi j of x. And yeah, of course, with momenta pj in 2p over L zd, say. Okay, so in this case, I have a very simple situation, namely I have a constant density throughout the box. So one parameter that defines the state is the density rho, number of particles divided by volume. And another important parameter is the so-called Fermi momentum, which is basically the highest momentum or also the average momentum that particles here occupy. So it's given as rho to the power 1 over d. Okay, so here you see in one dimension just n over L. In 2 dimensions you have a Fermi disk. It's square root of n over L, so it's always rho to the power 1 over d. Okay, so this is the kind of initial state I want to look at. And let me spend just 2 minutes to tell you what kind of scaling situation or what kind of parameters I have in mind for this model. And so I want to look at, so this model is very, it's well known, it's studied in lots of different contexts. This leads to this polaron models, Fermi polaron, also Bose polaron. Usually you take the mass of the tracer particle to be very high, and then you take a small coupling parameter here or so. But here I want to look at something different. Namely, I want to look at a situation where the masses are really of the same order of magnitude. So say they are both equal. Say they are both 1. And also h bar I've already set to 1 here. Okay, and then what I want to do is I first want to get rid of all finite size boundary effects. So I want to perform the thermodynamic limit of n and L to infinity with constant density. And then later I want to make the density very high. I want to look at very high densities rho. And at the same time I want to fix the scale of the test particle. For example, I want to have it to have momentum just of order 1. So say nabla of phi 0 is just bounded by a constant. Actually, I want to have a few more moments. It turns out that nabla to the 4 needs to be bounded for the main result to hold. I'll come to that in a minute. And well, maybe most important and maybe most surprising, what I want to do is I want to set the coupling constant equal to 1. So I do not want to have a small coupling. I want to have a strong coupling order 1. So this makes the situation is very different from the kind of stuff people usually consider. So the only parameters I've left here in my setup are basically the density rho and the time t. And now I want to know what happens to the dynamics of this test particle depending on the density and depending on the time scale. And before I come to that, let me talk for a minute about the physics behind that. So in physics, the situation, of course, does occur in lots of different setups. For example, if you have a very high density electron plasma and you have extra ions which fly through this plasma, what happens? Does the ion lose the energy to the plasma or not? Maybe that's for Percy very interesting. So this has actually been an interesting physical question in the 40s and later. So there's a paper by Fermi and Teller from 47 where they look at basically in a certain regime of a fusion reaction. So if you have a very high density electron plasma with a few ions flying through, what happens? Do the ions rather lose the energy to the plasma, or do they rather collide with each other and thus lead to a chain reaction? So this, I mean, I'm not claiming that this model answers that question, but it goes a little bit in the direction. So actually what happens is that for large densities, the electron gas becomes transparent. So this is very much the opposite of what would happen in a classical or in a bosonic gas. In a classical gas, if you make the density very high, there will be lots of collisions, and the particle will just do something that you can't describe anymore. Of course, on a correct scaling regime, you still can, and that is what people have done. This is works of Fröhlich and Gang about a Bose gas, where you have the small coupling parameter. Then you show that if the particle is fast enough above the speed of sound, then the particle does actually slow down and on the right time scale. So here it's the opposite effect. If you make the density higher, then the gas becomes more transparent, and the ions basically move through the gas freely. So for fermions, it's the opposite situation, which of course has to do with the fact that the Fermi sea is just an antisymmetric product of states of higher and higher energy that you have to occupy. Okay, I'll come in a minute to the more exact explanation.
Transparent means they hardly interact with it, right?
Yes. Basically, it just moves through freely.
So as if it weren't coupled at all to the
Yes, for very long times.
For a very long time. Gotcha.
Yes, and maybe let me make precise now what I mean by that. So maybe let me put the main result. Yeah, so let me put the main result here on the extra blackboard. So I want to compare the dynamics generated by this full Hamiltonian, sum of the minus Laplace xi plus the interaction between gas and tracer particle with a Hamiltonian, which is basically the free Hamiltonian with the correct phase factor. So you have also the free Hamiltonian here. And then, so what is the correct phase factor? So to first order, it should be just the mean field, the expectation value of the interaction in, say, the initial state. So to first order, it should be something called E0, which is really just the expectation value of this whole interaction, v of xi minus y, in the state omega 0, or say in the freely evolved state omega 0, which is still the same because it's just the phase factor of the time evolution. And in fact, because of the translation invariance, this here is independent of y. Yeah. So in the general case, what should be here should actually be the mean field, some field depending on y, something that influences the motion of the test particle y. In this case, it's not there because I look at the most simple situation where I just have a homogeneous initial state. For technical reasons, of course, it would be nicer to have a state which is not any filled Fermi sea should do.
Then you have some effect.
Then you would see some effect, yeah. So this is just it's just rho times the integral of v. So rho.
Yeah, and then
times
if
the
you
zero.
is there a higher order correction too that you would get?
Yeah, and that's the thing now. This is actually only with the mean field. The result, as I will state, it will not be true. There's an energy correction coming from so-called immediate recollisions. So there are certain recollisions that you have to sum up, and those lead to a correction in the energy. It actually lowers the mean field energy always. And let me denote that by E tilde A. Maybe let me come to that a little bit later. I mean, for now, this is just some constant depending actually on one parameter, which will appear in the main theorem in a minute. Let me just note that let me just note that always this correction is much smaller than the mean field. Also in one dimension, it's actually small the higher the density gets, so it really tends to 0 in our regime. In 2 dimensions, it's actually order 1. So it does play a significant role in 2 or higher dimensions. Okay, so maybe let me put here the main theorem. So as I already wrote here, for the initial conditions, I assume that nabla to the 4 phi 0 is bounded independent of rho and n and l. And then the statement is that for all a bigger 0, there's a constant Ca such that, so the norm distance between e to the minus I h t psi 0 and e to the minus I h tilde t psi 0. The time evolution generated by those two Hamiltonians, really the norm difference in the n plus 1 particle Hilbert space is bounded in the thermodynamic limit n comma L to infinity for constant density rho. Now by some constant Ca, and then I have here 1 plus t to the 3/2, and then we have a result in 2 dimension which says rho to the minus 1/8. Then you have here plus 3a for 2 dimensions, and you have a little bit better rho to the minus 1/4 plus 3a.
Yeah, I can't read that. Could you make that a little bit bigger?
This here, yeah,
well, this is the bottom one. So this is in the context.
Yeah. Rho to the minus 1/4 plus 3a for 1 dimension. Okay, I'll write this bigger too. So this is a rho to the minus 1/8 plus something very small in 2 dimensions. Rho to the minus 1/4 in 1 dimension.
Didn't you say previously it was dimension 3?
No, so 3 dimensions we actually cannot handle. For 3 dimensions, but I'll show you in a bit why. So for 3 dimensions it's unclear if this result even holds. That's because, well, in 3 dimensions, well, yeah, if I tell you why the result should hold, you'll see that it gets harder for this result to hold the higher the dimension is.
So what, now you have this alpha here. What is this?
Right, this a is really just technical. I mean, ideally I would like to let a go to 0, so I get the best possible bounds here, but then actually I have a constant here that depends on a that will blow up if a goes to 0.
A, okay.
Yeah, okay, so sorry, that's a Ca. So for all a bigger 0, there's a constant, but depending on a.
Yes.
And this constant appears here. And here I have an extra rho to the 3a or rho to the a here.
But you have to say that you want to say that exponent is actually smaller than 1.
Right. So ideally I would like to let a go to 0, so that this here disappears.
Wait, but can't you just put this e to the 3a to the constant?
Yeah, but I want to make the difference here. I mean, this is the rho dependence, this does not depend on rho.
Oh.
I want to make this difference.
Yeah, no, I understand that.
So, but I mean, you should really think of that as...
Rho, sorry, I forgot.
Sorry, yeah.
I thought it was e.
Oh, sorry, yeah, so this is...
Yeah, I get it now. So, thanks.
That's why.
Just for the record, you write a weird rho too.
Yeah, but I'm still a little bit.
Okay, yeah.
I'm still a little bit confused. You want that rho to be raised to a negative power,
Yes,
right?
yes.
So how do I know it's raised to a negative power? Is that minus sign?
Just
Oh, sorry, readability, is that the problem?
So
this is a rho to the minus 1/8
Yes.
plus 3, but forget about the 3, plus 3a. 3a. And a is this constant I have to choose.
But how do I know that constant isn't bigger than?
Yeah, so ideally you can let a go to 0.
You can let a.
You can choose a as small as you would like to.
Okay. So
But the
that's
problem-
what I didn't understand.
Right.
Not that there exists an a, but
Yes.
you can make a small
Yes.
as you like.
So
Otherwise,
yeah, of course. Otherwise it doesn't make sense. Yeah. And the whole reason why I wrote it down like this is because we cannot control this constant uniformly in a.
but then what's the point of 3?
Well, the 3 is you'll see in a minute because of this definition here. But I can put it away. Yeah, the 3 looks weird here. That's right. So let's just put an a here.
okay. So for all positive a,
And then let me put in
all
a
positive.
that here.
Okay.
Yeah. Okay.
Epsilon, right?
So really, you should think of it should be why?
So that's-
Why did I choose a? It should be
that's
epsilon.
what I'm
Yes.
saying.
Yes.
That's
Sorry.
what I'm saying that
Yes.
all I see. It says for all a.
Yeah.
So of course you want a big. You want
Sorry.
a small as possible. Gosh, I just couldn't read it all.
Sorry. Yeah.
I probably.
Ah, now I get it. Okay.
I can't change it now.
Okay.
So that means that if the density is very high,
Right.
then that product is very small.
Exactly. Say for times of order 1, for sure, but you can even go to longer times.
Yeah.
Longer times in row. So even though the density gets very, very big, you can extend the results to very long times.
Now, is there expected to be another correction beyond what you have there, where I could,
Well, of course, in principle, there are lots of corrections. Yeah.
Do
I
you
mean,
know what they are? I mean,
no. That's how far we could get. Yeah.
no, but I mean, is there something like that in the physics literature that tells you what you should expect, or?
Yeah, I mean, the next correction should, of course, be should describe the energy loss, right?
Yeah.
So there should be a Lindblad type equation that describes the energy loss. But you'll see also in a minute why it's really, really hard in this case to write down such an equation, because we don't have a small coupling parameter.
Yeah.
We cannot simply do an order by order expansion and then look at the first couple of orders and see what's the next to leading order correction. But it's more complicated here because we don't have this small parameter, but we sort of have to get it out
I see.
from the dynamics. You have to get it out of the dynamics.
No, if you don't have a small parameter, then it's going to be tough.
Yeah. And let me maybe just to be complete, write down what this energy correction here is. So this E tilde A is given as the thermodynamic limit. Let me just abbreviate this by limit TD. That's this kind of limit of L to the minus D sum k equals 1 to n, and the sum L equal n plus 1 to infinity. So this will sum over all momenta inside the Fermi sphere. This will sum over all momenta outside the Fermi sphere. And then here you have a V hat, the Fourier transform of V, of pk minus pl squared, divided by the energy difference pl square minus pk square. And then you have to cut off this summation, or in the thermodynamic limit integration. Okay, this is a bit technical now, but let me write it down to be complete. So as soon as PL minus PK becomes bigger than rho to the A, you cut off. And also when the difference in the momenta, let me write it here, when the difference in the absolute values of the momenta becomes very, very small, you also cut off. So theta is just the usual step function. 1 for positive x, and 0 otherwise. But you'll actually, when I come to a little bit of the sketch of the proof, you'll see why these kind of theta functions should appear and why they are important. They basically tell you something about this phase difference here. Okay, so this is energy correction.
So that makes it clear that your denominators are well defined, or what?
Yeah, and of the right order of magnitude in particular. Yeah. So yeah, I mean, these kind of corrections are well known. They also appear in other kinds of proofs. For example, there's this proof of quantum diffusion by Erdős, Yau, and Salmhofer. They also have an extra energy corrections coming from so-called immediate recollisions. So those are basically.
This is immediate recollision here?
Yeah, this comes from the immediate recollisions. It's exactly necessary to cancel the contribution from the immediate recollisions.
Are these like what I would call ladder graphs? I mean, that's what they have. You don't know the
Right.
terminology.
I'm not so familiar with the terminology, but it sounds right. Okay, I can easily write down. I mean, immediate collisions are just one collision you lift the particle, and with the next collision you put it back in the same place.
Yeah.
That can happen lots of times. So that's
particle with the it recollides with the C, the Fermi C, right? So this,
right.
This is and then goes back. Yeah,
it goes back to its initial state. Yeah.
I think that must be the same thing.
Yeah. So this is similar.
It must be related.
Right. Yeah. And yeah.
It should be small in one dimension, you said, right?
It's small in one dimension. Yeah.
Why is that?
So this difference here, PL square minus PK square. It's basically PL minus PK, PL plus PK. And PL plus PK is always bigger than the Fermi momentum, because the interaction potential was assumed to be C infinity, so basically there can only be interactions with finite momentum, order 1 momentum transfer. So this V hat decays very fast. Actually, by the Pelli-Wiener theorem, it decays exponentially fast after a scale of order 1. So PL and PK have to be very close to each other. So there cannot be any interaction within the Fermi sea because all the states that are occupied, there can only be interactions on the Fermi surface. And so PL and PK has to be of the order of magnitude of the Fermi radius plus minus 1. So this is here bigger than the Fermi radius. And exactly here you see if this, on the other hand, becomes very, very small, then I have a problem here. So I have to make sure that this doesn't become too small. And that will also appear later in the proof. But here, from here, I get the small factor of the Fermi momentum.
Maybe you're
But then, but then again, I have to sum over all these contributions. So this,
That's like an integral, essentially, right?
in 2 dimensions, in 2 dimensions, it gives me the Fermi surface basically, which in 1 dimension is just a point. So in 1 dimension, I get a 1 over kf, but in 2 dimensions, it's kf, the surface.
Yeah, and
So I get
is
something
that
out of
an
it.
integral that diverges in 3 dimensions or what?
In rho it diverges. Yes. It'll become large in rho.
Yeah, so that's why you don't.
Yeah, maybe let me.
2 dimensions.
Yeah, okay, but directly the energy correction is not really the reason. It's already the reason comes already before.
Okay.
I will explain it in a minute.
Yeah, because this would be an infrared problem, so you'd expect that increasing the dimension should make things better.
So you mean this expression depends on the infrared behavior?
Could make this, what could make this big is when you have PK close to PL.
I would say this effect basically, I mean the area that you have to exclude here it turns out to be in fact very, very small. So most of the momenta are actually order 1 apart from each other. So that's how you should think. So this should always be of the order of kf, roughly. Of course, there are problems when momentum difference becomes small, but you should think of it as being of the order of kf.
No, I'm just saying that,
But then,
so why would increasing the dimension make things worse?
because with higher dimension, the Fermi surface becomes bigger. Well, kf, the Fermi surface depending on kf becomes bigger, not in rho, sorry, yeah. With kf it becomes bigger. But of course the Fermi, of course you always have this relation. Fermi momentum is always the density to the one, it becomes big because the density becomes big, yeah.
Okay.
Yeah. All right. Maybe 1 or 2 more remarks. I mean, I already told you it's in sharp contrast to a bosonic gas, where you would expect rather the opposite behavior. You would rather expect maybe a T times rho bound, because you have all these collisions and a strong coupling. Right. Also, the thermodynamic limit we take only to eliminate finite size and boundary effects, which we don't really want to have. So this is not a big problem here because our state is so simple. We can easily switch to the thermodynamic limit. And then it might seem a little bit surprising that we actually look at the norm difference here on the full Hilbert space rather than, say, reduced densities, some macroscopic object. But in this case, this is really the right thing that we want to consider because we only want to follow one single particle. So as soon, say, as there is a collision between one gas particle, which significantly disturbs the test particle, already you would say this approximation for the test particle does not hold anymore. So you really want to control.
That's the full Hilbert space.
Yes.
That's the full Hilbert space.
Yes. You really want to control the full norm.
Yeah.
As soon as you have a significant collision, your result will fail.
Yeah. So I mean, you might imagine you would get better estimates or something if you didn't take such a strong norm, right?
But here I just have one single particle that I want to follow, basically. I only want to follow this test particle. So if I take, that norm or the reduced density of the test particle only, it won't matter so much.
For that, I guess it's very important that the particles in the bath don't interact. They only interact with
Right. So if there were additional interaction, I'd have to appropriately take care of that. Not all particles will follow the effective evolution because of the mutual interaction. So that's a much more difficult problem that we cannot get into right now. Yeah. Yeah, so this is very, very much simplified. You have no interaction in the gas. Yeah.
Right. I mean, you'd expect that you'd want to look at a different norm if you had interactions.
You would have to look at a different norm, yes.
Something happens really far away from your tracing.
Yeah, of course, yeah. Yeah, you would look at something local maybe. Yeah, exactly. Yeah, yeah, very much. Right, so, okay, so why does this result really hold, although we don't have any kind of small coupling? Well, for one, you have energy momentum conservation, which really restricts the kind of transitions you can have in the Fermi gas, which I will explain in more detail in a minute. So that means that only few particles can actually interact. Well, already as we noted here, only the particles on the Fermi surface are actually relevant, but it will turn out to be much less than that. And then, because the interaction is only here at this Fermi surface, it's only interacting with particles which are very, very, very fast, momentum kf. So basically the interaction is only for a very short time. And that makes the interaction effectively small.
I see. So the particles on the surface are really
yes.
have a high momentum.
Yes.
They somehow average out to do something less serious. So
Right. I mean, right. Yeah. So of course also it's kind of really explained classically. Classically, if you have two particles run very fast, it's a big effect. But quantum mechanically, it's not, because the momenta are so different. You have the phase scans.
Theory, high frequency often has less effect than in classical mechanics.
Right, high frequency, yes, and that's exactly the effect here also. The high frequency of the plane waves. Yeah, yeah, exactly. Yeah,
that averages out.
Yeah.
Why is it mostly the particles around the Fermi surface that interact with the tracing?
Yeah, let me come to that now. So let me talk a little bit about conservation laws and the spectrum. So maybe let me start with the case of one dimension. So let me draw here the space of possible occupied momenta. So here you have 0. Say here you have the Fermi momentum. You have all symmetrically occupied. Here you have minus the Fermi momentum. And suppose you have here the initial momentum of the y particle. Py, say it's just one definite momentum in one direction, just for this picture. Right, so because of momentum conservation, you cannot, well, first of all, because of the Fermi pressure, you cannot just pull out a particle here and put it here, because these states are all occupied. That's the antisymmetry of the wave function. That's the Fermi pressure. So what you have to do is you have to, you only have available a momentum of order 1 here, but this is actually very, very large. So you have to excite particles here close to the Fermi surface. For example, if you would like to transfer, say, all the momentum of the tracer particle to an extra particle, you have to do it here at the surface because of momentum conservation. So you only can excite particles in this range because of momentum conservation. And of course, because the interaction potential is such that the momentum transfer in a collision is of order 1. If, for example, I would choose as an interaction a delta interaction or so, it would have components in all of momentum space, and I wouldn't have this dampening effect. But here I have a nice order 1 potential. Coulomb might also be different because you have this long range and short range problems. So right now we only deal with these nice bounded kind of interactions. But then, so this is basically what follows from momentum conservation, but you also have energy conservation. And let's look at the, let's, for example, look at one of these transitions. Suppose you have here the tracer particle. It collides with one of the particles in the gas, leaves a hole behind, and makes an extra particle outside of the Fermi sea. What are the corresponding energies? So the initial energy would just be py squared, the kinetic energy of the test particle, plus the kinetic energy of the Fermi sea. which is just n times the Fermi momentum squared, plus you will have a potential energy, say just the mean field energy rho times v hat of 0. But that won't play that much of a role here.
What's that say? It's rho times what?
So it rho times v hat of 0. So v hat of 0 is the 0th Fourier component of v, integral of v.
Yeah.
And suppose the Fermi C is really filled symmetrically, so the initial momentum, so the initial total energy and the initial total momentum is just the momentum of the test particle. But then after this collision, you have a final total energy, which is now, well, suppose the test particle has given away all its momentum, so it doesn't have any kinetic energy anymore. And then you have the kinetic energy of the Fermi C, but you have taken out a particle with momentum, say, pk. You have taken momentum pk square out, and you have added a particle with momentum pk plus py. Plus you still have this constant mean field. So this is now the initial energy, p square and kf square, this contribution, this p square cancelled with this p square, so only the two pk, py remains. So now if I imagine py is some quantity of order 1 and pk is close to the Fermi surface. So this is always of order kf, so this is very, very large. So I can never fulfill energy conservation. All these kinds of collisions, they are not compatible with energy conservation. So the energy difference after this collision will always be really, really large. Right, there's an extra kf factor. Delta E will grow, will be large. I don't want that. I want a collision that conserves the energy. So that basically says that in one dimension, there are not really any transitions simply because of conservation laws. So in one dimension, this result might actually not seem so surprising because, I mean, there's already this mechanism which forbids basically all kinds of transitions.
So it forbids any kind of interaction, you're saying?
Basically. I mean, this is of course just an average picture.
No, yeah.
We have quantum mechanics, but that's basically it, yeah. So in one dimension, you might actually also be able to do a different kind of argument, which is really based on that, where you might even get something better. I'm not sure. So yeah. Anyway, for one dimension, you have an additional mechanism. But I now want to show you that for 2 dimensions, you do not have that. So for 2 dimensions, you have a whole Fermi sphere, px, py. So here you have again the Fermi momentum. And suppose again you have here the initial momentum of the test particle. Suppose it goes in the x direction, just for simplicity. And now we already know that here I cannot really make transitions. But what about here? So I make a transition close to the poles of this Fermi sphere, say with momentum pk, and after that I have here momentum py plus pk. Okay, I again want to transfer all the momentum of the test particle to the excited electron, and now the energy difference, final total energy minus initial total energy. Well, I've already calculated here, except that now it's a scalar product of pk with py. So, and suppose p of the y particle goes in the x direction. I could, for example, choose the pk. So say py is some 0. No, what is the x direction? Is some p0, 0. Then I can choose pk to be just 0 kf, for example, and I would have an energy conserving transition. And basically, I don't have to choose exactly exactly that particle here, but there's a whole region of particles where I can make transitions.
When you say this, you take, even in one dimension, when you say you're taking a particular particle, a particular momentum, you're assuming that momentum is somehow or one or something.
Exactly. I mean, that's what I've assumed here. Yeah.
And,
of course, you have to average over all momenta in the end. Yeah.
but that just says that I mean, I'm just saying that if I had small momentum, I wouldn't see much violation, right? I would not see a violation of energy conservation.
If the momentum were very, very, very small,
Yeah.
yeah, it would have to be
multiplied by pk.
it have to be small compared to the density.
Yeah.
Sure.
Don't care about that.
You could look at such regimes. I mean, you could look at such regimes where, for example, the mass becomes, in this case, you would like to have it very, very small.
Yeah.
You could look at such a regime, but yeah, for now, I mean, the scale of the test particle should just be the macroscopic scale. In this case, we really want to see an ion macroscopically flying through a gas. Yeah. Mm-hmm.
In 2 dimensions, there's no such argument. You're saying.
As in 1 dimension. Yeah. Yeah. So in 2 dimensions, you have a whole region of particles that you can actually interact with. But then again, there's this additional effect. Well, first of all, the velocity is big, so actually the Boltzmann cylinder, the number of possible collisions becomes again larger. But then again, quantum mechanically, because of this high velocity, the coupling is effectively small. So it becomes smaller again.
You have a small angle at which this can happen.
Yeah, so this is much, much smaller than the whole Fermi sea. It's even much smaller than the whole Fermi surface, but it's still it's still a big number of particles.
It goes to a point as rho goes to infinity, right?
Yes, that is true. But again, the particles are so fast that the number of possible collisions would again be at least order 1. Yeah, basically this goes to like 1 over kf.
Yeah, right.
But then again, the velocities are kf. So basically, you would say the Boltzmann cylinder is really of order 1. And then there's this additional effect that the transition probabilities are small, which make the whole thing work. Yeah, so what this argument also shows is that our initial state really lies on top, if you look at the total momentum versus the total energy, on top of a continuous fiber of states, which can go up to energy 0. So in principle, the tracer particle could lose all its energy to the gas, which it also will do after very, very long times. But here we show that for surprisingly long times, or these kind of long times, this does not happen. So we show that this resonance here that we start with is really stable for these time scales.
But you don't have a theorem yet that says that it does go to 0, or is that obvious? That it does. Eventually, it does go to 0.
Right, we've looked around a bit and see if there's lots of work in this directions with all kinds of different systems, harmonic oscillators coupled to the extra particle. So in this case, where we have this this continuum of states and the excitations are very high velocity, we couldn't find a result that would. We couldn't find an abstract result that would tell us that in this situation it's true. But we are, but we are sure that it happens.
Sure
of course, of course. Well, that's the next thing maybe we want to look at, really prove that it goes to 0.
Know that, right?
Yeah. Well, but we're pretty sure. Yeah.
Okay.
It must have, of course.
I've been asking you a few times, but I just wanted to be sure you hadn't changed your mind.
No. Okay. Okay, so now I could come to a little bit more details of the proof. Let me maybe erase that. So as I already said, we don't have a small coupling parameter, so it's really hard to make an order-by-order expansion and then cut it off at some point and estimate the error term. So this didn't really work here, because at some point we have to take into account the full time evolution, and we have to estimate it brutally. So actually what we do, let me call it a sketch of proof. So what we do is we, of course, we make a Duhamel expansion. There's no other technique. That's the most obvious technique. And we have to do it up to third order for certain types of transitions to get this result. And then after the third order, we really have to control and cut off the whole time evolution, and the rest of the experiment has to be small enough in order to control what we throw away.
You're expanding in V.
Yeah, so let me write down how I expand. So let me write down here the difference that I would like to control. Evolution with H, evolution with H tilde. So now I write down the Duhamel expansion, minus I integral ds. I have an e to the I. Let me write here H tilde, t minus s. And then I want to control in H minus H tilde, which is the total interaction minus the mean field and the energy correction. So here, let me also write H tilde here and put all the rest in an extra term. So here I have e to the I h t minus s minus e to the I h tilde t minus s h minus h tilde e to the minus I h tilde s psi 0. So this would be a first order expansion of what I want to control. Right, so here I just wrote this term minus this term, just I inserted the 0 here, and this is really the Duhamel expansion. So let me maybe for simplicity look at, well, as I said, the real expansion is more complicated. You have to go to third order.
Just go on first order here, right?
This is just first order.
Yeah,
so let me.
But you need to do three.
Right.
You need to do this several times.
Yeah. So let me maybe for simplicity, just for a couple of minutes, discuss one example term, and let me for simplicity discuss this most simple term, which is where I do not have to control the full time evolution.
Yeah.
So at some point I'll have to do it, but let me, for simplicity, only look at that term where I don't have to do it. So here, right, so let me maybe, so as an example, let me look at star, which is integral e to the, I think I made a sign over here. E to the I h tilde s h minus h tilde e to the minus I h tilde s. Okay, that here I can throw away when I take the norm by unitarity. So let me look at that example term. So yeah, h minus h tilde is the difference v minus e0 plus this energy correction. So this is really basically it's the interaction minus its expectation value in the freely evolved state. That's basically here a typical mean field term up to this energy correction. And maybe let me so this energy correction is not relevant for that term. It has to be used to cancel other terms later. So maybe let me, for simplicity, estimate here only the difference between V and E0. Okay, let me spend.
Because the other one's higher order, so.
The other one will be used to cancel a higher order term. Yeah. Let me spend just 1 or 2 minutes to write down the expression so you really see where the different types of terms come from. So here you have the integral of what? So I h tilde s. Then you have a sum, I equal 1 to n, of the v of xi minus y minus, if I take the sum out, e0 divided by n. Okay, and let me make some space here. Okay, now I just standard argument. I want to look at all the kinds of possible transitions between possible momenta. So I want to introduce, I want to insert here and here, here and here, two identities, sum of all possible momenta, phi k, in, so we are projecting on all the possible momenta in the xi variable.
So I don't know, how did you get this, how did you get this sum here? I didn't know where the sum came from.
Sorry, okay, so sorry, this v here is just the, sorry, this is the total.
Of course, yes.
Sorry, I didn't introduce that notation. Yeah, that's it. Sorry. I didn't introduce it, sorry. Okay. Right, so this is sum over, well, of course, over all variables.
All the interaction between the particles,
Yeah.
the J particle.
But then, if I introduce these two identities, and psi 0 is my initial state, phi 0 tensor omega 0. So it means from the identity here, the k has to come from inside the Fermi sea. Only I have to annihilate an occupied momenta here. But the particles which I then add again, the other k particle has to come from outside the Fermi sea. Because if it's just an antisymmetric product, I cannot add the same wave function in the sea, then the antisymmetric product is 0. So basically all that contributes is you still have these time evolutions here. Then you have an, let me call it a sum over k1 to n. Let me use the same notation as there. L goes over the momenta outside. Of, here I have an phi L, v of x minus y phi k. And this is now the scalar product. Well,
So you're just going
scalar
right
product
down
x.
to you're writing it out in terms of the eigenstates.
Yeah.
The full thing.
Yeah.
You don't try to do anything else. I mean, maybe there's nothing else you can do. I don't know.
Well, for now,
You can't write down a propagator so easily. It doesn't have a nice form.
well, the tilde propagators, yes. In this eigenbasis, yeah.
Non-interacting problem.
That's what I'm doing. Yeah. But the full propagator, no, I don't know. This is very, very simple. This is not sophisticated.
Okay.
Just very.
Okay, well, I was just wondering whether there's some other way to do it, but fine.
Right. For now, this is just simple rewriting, so I can get a handle of these terms. Yeah. So, okay. And then what have I left? I have an. Well, basically, if I sum over all these possible particle variables again, I get here a dagger L, a k term, if I write it in second quantization. So the sum over all I, sum over all I of phi L, phi k in the xi variable. So it just annihilates a k particle in the sea and creates a particle outside the sea. Now there's also a contribution where L is equal to k, but this cancels exactly this mean field here. That's exactly how I define the mean field.
Diagonal terms.
Yeah. That's why I need to add the correct phase factor here. And then you have again the time evolution psi 0. Okay, so let me write down one more step, and then you'll see how we can estimate that. So this is time integral. Okay, so what happens now here? So this state is factorized. This evolution also factorizes. So basically here I get the free evolution of the y particle. I get all the phase factors from the x particles in the C. But then I take out a k particle and add an extra L particle, and I get the new phase factors of those. So the L and the k energy phase factors are left over. So maybe let me write it down as from the definition of the Fourier transform in a large box, I get a 1 over L to the d factor here. And then, so I get here the v hat of PL minus PK.
So the V.
So here it's just the Fourier transform of L minus K. With a definition that I get a 1 over L to the D out. And then, so what do I have? So let's look first at what happens to the Y particle. So here I get, okay, let's start from this direction. Here I get a free propagator, e to the I minus nabla ys. Then here I do get a phase vector now. Namely, I get, because it's at position y, x minus y. So I get an e to the I pk, pl minus pk times y. And again I get the free propagator, e to the minus I minus nabla ys, acting on phi 0. And I get the tensor product with, okay, this is now the important thing, what happens with the C. Yeah, as I said, the phase factor of the kth variable is left over, e to the minus.
Somehow what you've got is just the ordinary Fourier transform
Yeah,
of the potential itself.
Yeah, that's Fourier transform, yeah. In the basis, which is really the Fourier basis in this case, what I start with. Yeah. So in general, if you do not take the free Fermi C here, you might think of having a generalized kind of Fourier transform here. You can do some things with that, but we're not able to do the full thing. So you get an e to the minus I eks, and from the L factor you get the same with a different sign. So you get an ek minus els. Well, and all the other phase factors cancel again, all those that are not L and K. And of course, the mean field phase also cancels. So here you get again omega 0. Okay, so this is really the kind of expression that you have. And now, so now we see that that the smallness really comes from this highly oscillating phase factor, which is exactly, as I already wrote down here, you should think of as being of order kf, unless these two here become very, very small. So suppose those are of order 1. They cannot be bigger than order 1, but suppose they are of order 1 and don't become too small. Then you can do a partial integration here, and you get a 1 over kf from this integral. And yeah, maybe since I'm...
When you have it, you have it.
Oh, sorry.
Why is that highly, I mean, aren't there values where that difference is small?
Yes, there are. When the absolute values of the momenta are very close to each other. Yeah, so that you have to be careful about. That you have to cut out of your later of your integration and have to treat separately. Yeah, they're basically these stationary phases that you have to be careful about. Yes. But those have a very small integration volume, because those have to be small in rho. Okay. This factor has to be small in rho, and this makes the volume small, such that again it'll be of the right order. Well, maybe as a last sentence, let me just say, so if I now do a partial integration, I get a 1 over the phase factor here, which will give me a 1 over kf. And I will get a time derivative of this whole thing here. But that is not so bad, because basically it just gives you, well, if I take a time derivative, I get a Laplace here, so I get once the momentum difference, which again I should think of as being order 1, and I get a nabla on these y particles, so I get the initial momentum in, which I assume is order 1. And of course, so yeah, the argument is...
So you're doing the integration by parts now?
Yeah.
Okay.
So the argument is finished by saying that the norm squared of that is really 1 over L to the D sum here inside the Fermi sea, some momenta outside the Fermi sea. And then I have v hat squared, because those... sorry, I forgot the a very important thing here, of course, the L dagger AK omega 0. So for different L and Ks, those states are orthogonal to each other. So that's why when I take the square, I only get one sum of each Ks and Ls. And then here I get, well, let me maybe approximate here. So here, as I said, approximately, if I square this thing and do the partial integration, I get a 1 over kf. And suppose I've squared this whole thing, I get a 1 over kf square. And then, as I already said in the beginning, so now you have to sum up all these possible interactions, which are basically the variance of the interaction potential here. And that is, well, for these kind of interaction potentials, as big as the Fermi surface. Kf to the power d minus 1 in d dimensions. So and here then you see in one dimension you get times t square if I take a square. So in one dimension you get something really nice. You get a 1 over kf square factor times t square. So this order would actually be much better than our main result, but doesn't become as good if you go to higher orders. In two dimensions you also get something small, kf over kf square, 1 over kf, which is nice. But in 3 dimensions the fluctuations are of the order kf square, which is the same order as the phase factor. So there's
So
from
you're
that.
already so you're already dead in first order perturbation theory somehow. This technique, right? Yeah.
Exactly, yeah. Yeah, and as I said, the immediate recollisions.
The second order.
Right, that's second order. So basically, what you do is you do this expansion twice.
Yep.
Then you get lots of different possibilities of transitions. So you can. This is momentum. These are all occupied. You can have if you have two. If you do this expansion twice, you can have this effect where you get one particle out and another particle out. This is the kind of transition where you have to expand another time. And there's also the kind of transition where, well, you take one particle out and you put it, after this free time evolution, you put it back in. And this is exactly that kind of recollision that is actually not small and that you have to cancel with these energy correction. So this was also very, this made this whole proof also very hard. In the beginning we didn't have this energy correction, so we were wondering, why doesn't it work? And then,
Stuck, right?
then you see there is actually a term that doesn't get small, that you have to cancel with the energy correction. Right. Yeah, so that's how you
So
roughly
I
get that
don't-
result.
Just the first order perturbation theory, I could go to I'd get a better answer, right? Is that,
Sorry, if,
if I just looked at first order,
yeah.
I would get a better answer, right?
Exactly, but actually I've cheated you here a little bit because, I mean, exactly that term you would like to take the scalar product with psi 0 here.
Mm-hmm.
And of course, if you're interested in the norm difference, you only take the real part of that.
Yes.
So actually this term actually doesn't contribute. But I showed it to you anyway because all the other terms are very, very similar, only an additional step more complicated. And actually, well, it does contribute in the sense that you have this energy correction here. Well, so if you do, yeah, what I mean is if you do the second order, you have energy correction. So you have one term which looks like energy correction times this. So you still actually do have to estimate that.
So you have all kinds of cutoffs so that you can, well, I guess you're not letting time get to be too big, right? Because you don't know what happens after some time.
Exactly. I mean, this. I mean, after.
So that's the reason you can do Hamel to some extent, and live,
Right.
live with the answer.
Right. So after this right-hand side becomes order 1, this bound doesn't say anything anymore.
Stop.
Sure. Yeah. Right. So I mean, basically, what I wanted to convey here is And there's some interesting physics behind this model and behind the scaling behavior. And the mathematics is actually very, very hard because you have to get out of the dynamics of the system. You have to get out a dynamically small coupling parameter.
Yeah.
You cannot just put it in there. And that makes mathematics more involved. Yeah. Yes, well, thank you.
All right, thank you.